Okay, this is the problem we worked on in class. So this is a first degree linear differential equation with variable coefficients of x to the third in front of the y. And so this is also not a Cauchy-Euler equation. So what we're going to do is we're going to solve this using the approach that y is going to equal a sum of from n equals 0 to infinity of c sub n x to the n. Okay, and therefore y prime is equal to the sum from n equals 0 to infinity of n c sub n x to the n minus 1. That's just using the power rule because you can do a derivative of a series term by term. And if you needed to do a second derivative, it would just be n times n minus 1 c sub n x to the n minus 2. And then we're going to put these derivatives into this original differential equation and pick some values and recursively figure out what this is going to be. So I'm going to give you the first four terms of this solution. I'll also give you the explicit solution as well. Okay, so uh, let's put the two derivatives here into uh, the problem here. So we have y prime, which is going to be the sum. Oh, and by the way, we don't want to start at n equals 0 because when n equals 0, you notice that y prime is also 0. So it'd probably be better to start at 1 with the derivative. So we're going to take the sum from n equals 1 to infinity of n c sub n x to the n minus 1. And then we're going to add x to the third times the original y, which is the sum of n equals 0 to infinity of c sub n x to the n, and this has to equal 0. Okay, so this is the original problem. Now we'll do a little bit of simplifying here. This is n equals 1 to infinity of n c sub n x to the n minus 1. Plus, we can put the x cubed in, so we have the sum of n equals 0 to infinity of c sub n x to the n plus 3, and this equals 0. Now, in order to make this work out right, we want to put these two summations together so we can equate some coefficients. Okay, but again, there are two things we need to be able to do in order to put two series together. In order to put two series together, the first thing we need to do, I'll write that a little bit better. The first thing we need to do, first thing, is to sync the variables, sync VAR. So we'll do that first. So what this means is if you notice when we start each of these series, the first series starts at 0 because 1 minus 1 is 0, x is 0, and the second series starts at 3. So what we have to do is we need to take out the first three terms of this series so then the x's sync up. So when we let n equals 1, you notice here that when x is 1, we get 1c c sub 1 x to the 0. So that's going to be c sub 1 plus, and then we're going to let n equal 2. So this is going to be 2c sub 2x. And then we're going to let n equal 3. So this is going to be 3c sub 3x squared. Now, then when we put the rest of this one, so we did 1, 2, 3. So now n is going to equal 4 to infinity of n c sub n x to the n minus 1 plus the other series, which we haven't touched yet, n equals 0 to infinity c sub n x to the n plus 3, and this equals 0. Now if you notice, the two series the x's are in sync, because when you start at 4, you're at x to the third, and when you start at 0, you're at x to the third. But we can't forget these three terms. Okay? And then the other thing that you have to do is you have to get the indices have to be equal. So the second thing is that the index has to be equal for both of these, and they're not, because you can't add these two series up if they start at different numbers. Okay, so what we do is, in order to do that, is we just let k equal the powers, because if the x's are aligned, and if you let k equal the powers, then that will make the indices equal. So we're going to let k equal n minus 1 for this one. And then we're going to let me erase this. We're going to let k, we're going to let k equal, let k equal n plus 3 for this one. And now you'll see that we have c1 plus 2c2x plus 3c3x squared plus, now we have the sum from, okay, if n starts at 4, when you put 4 in here, 4 minus 1 is 3, so that means k is equal to 3 to infinity. Now what is n? If you again add 1, then n is k plus 1, c sub k plus 1, x to the k, plus, and now we're going to do this one, sum n equals 0, so 0 plus 3 is 3, so this is k plus 3 to infinity of c sub n is k minus 3, so k minus 3, x to the k, and this equals 0. So take a look at that, because I need to clear the screen here because I've run out of room. So if you notice here, we have these first three terms, and you notice these three, they both start at k plus 3. They both start at 3. So the indices match and the powers match, and that's how you do that. Okay, so you have to take enough terms out of one of them, the one that has the higher x's, until the x's sync up. Once the x's sync up, you just let k equal the exponents of the x's. Do the substitution so it's all in terms of k. All right, so now I'm going to clear this, and then we're going to continue on. Oh, actually, I think I can kind of do some of this here. Now what we're going to do is we're going to equate coefficients. Okay, this all equals 0, but even if it wasn't homogeneous and it equaled other things, just equate the coefficients. That's fine. Okay, so equating the coefficients, everything is equal to 0, which means here's our only constant, c1. So let c1 therefore must equal 0. There are no x's on the right side, so therefore c2 has to equal 0. There are no x squares on the other side, so c3 has to equal 0. Okay, now, and if you notice for the summation part, you can factor out an xk, which means, therefore, that that if you take xk and you factor that out of each of these and put a sum with each of them, that all those coefficients have to equal 0 as well. So what this means is that since we can put these two together now, we have plus the sum of k equals 3 to infinity of k plus 1, ck plus 1, plus ck minus 3, and then this is all being multiplied by x to the k, and this whole thing here is equal to 0. So this must mean that this summation has to be 0, which means, of course, this big coefficient has to be 0. And so I'll write that on the next page. So what we have here then is we have k plus 1 times ck plus 1 plus some ck minus 3 has to equal 0. Okay? And then solve for the higher k, which is k plus 1, because that will make the recursive work better, which means ck plus 1 equals negative ck minus 3 over k plus 1. And this is what we're going to use to do our recursives. Okay? So let's start doing our recursives. When k is equal to, well, notice when k is equal to 0, that's c1. So we don't know c0. Okay, but we do know c1 because we've already did it on the previous page. c1 is 0. When k equals 1, that's c2. That's already 0. When k is equal to 2, that is c3, and that's already equal to 0. That's already given. Now, when k is equal to 4, this is the one we don't know yet. Okay, or k equals to 3. I was jumping ahead. I was thinking C4. So when k is equal to 3, then we have C4 is equal to negative C sub 0 over 3 plus 1, which is 4. So this equals negative 1/4 C sub 0. Now, hopefully you understand that C5 through C7 are also going to equal 0 because they're all going to be based on C1, 2, and 3, which are already 0. Okay, and so that leads us to C8. C8, which is going to be k equals 7, by the way. So that's going to equal C4, which is non-zero, divided by 7 plus 1 is 8. But of course, this is 1/8 times C4 is negative 1/4 C0. And so we have this, which is equal to negative 1/32. Okay. Wait a minute, I forgot the negative sign. Negative, negative, so that's positive 1/32 C0. C9 through C11 are 0. C12 is equal to negative, that's going to be C8 over 13, to over 12, because K is 11 to get C12, which is equal to negative 1/12 times C8, which is 1/32 C0. Which is equal to negative 1 over 384 C0. And I'm going to clear. C13 through C15 is equal to 0. And that leads us to C16, which is negative C16 is negative C12, negative C12 is negative C12 divided by 16, which is equal to negative 1/16 times C12 over 384, which equals negative C12 over, I'm actually figuring this out, 6,144. Okay, so remembering the original problem, y equals the sum of n equals 0 to infinity of c sub n x to the n. This is going to equal, of course, when you start at 0, c0 plus c1x plus c2x squared plus c3x to the third plus dot 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 dot. So in this problem, y equals, we don't know c0, that's our constant, so we put that in, plus, actually I think it's going to be minus, because c1 is 0, c2 is 0, c3 is 0, but c4 is minus, I do believe that was 1/12. No, it was 1/4. Minus 1/4. It's hard when I don't have the previous work. 1/4 C0, that's going to be x to the fourth, because that's the fourth term. Plus, and then I think it was C8 over 32, x to the eighth was the next term, minus C0, not C8. C0 minus C0 over, this is x to the 12th, so this is over 384, x to the 12th. That's the first four terms, but if I did the five terms, because I actually did it, minus plus minus C16, that's minus, that was plus up here, plus C0 over, that was C0, 6,194 x to the 16th. If you're curious on what this is as an explicit formula, this was the sum, you could put the C0 up front, of n equals 0 to infinity of negative x to the fourth over 4 to the nth power times 1 over n factorial, if you're curious. But I may just be asking for the first 3 or 4 terms. Okay, that's it. Thank you.